In this video, we're going to review the information that we saw at the beginning of semester about infinite series, and we're going to go a little bit further in a new test for the convergence of series called the nth term test, or the test for divergence. So let's start with this little review. So the first thing that we saw is the format. We saw some sigma rules that we're not going to review here, but we had this as an infinite series where a sub n is another way of writing a function rule, f of n, and a sub n is called the nth term of the series. And we had this starting at 1, but could start at other values, very typically as well at n equals 0. N equals 1 and n equals 0 are the most common starting point for series, but they really, they can start at any integer value. So we also saw s sub n, which is not the same as a sub n. S sub n is the nth partial sum, and its definition was the sum of the first n terms. Right? Partial, because if you're going to infinity, adding up n terms is only part of the sum. So we had the sum from I equals 1 to n of a sub I is the sigma notation for this sum here. And then we also noticed that if you take just the first n minus 1 of them, then this is s sub n minus 1. And so we had this relationship. We had s sub n is s sub n minus 1 plus a sub n. Now the definition of convergence for a series was in terms of this partial sum. If we are adding up n terms and we let n go to infinity, then that is like adding up all the terms. So if this limit exists, and that's a big if this limit exists, the series is called convergent. And the limit value is the series value. We say that they are equal. If the limit does not exist, however, the series is called divergent. And those are the same two terms, convergent and divergent, that we have used subsequently for improper integrals as well. So we'd seen two types of series. We'd seen the telescoping series, and what you do in the telescoping series is you apply this definition of convergence, this one right here. You apply that directly. And so let's go and look at an example to refresh our memory about the telescoping series. So if we had a series that looked like this, so we're adding up infinitely many terms, all of which fit this function rule here, plugging in n for the different values. Well, the first thing that we did, and we've done this subsequently as well, was a partial fraction decomposition. So I skipped the whole step of that here, but this is the result of the partial fraction decomposition. So this series ends up by being the series of, if we split this up, 1 over n plus 4 minus 1 over n plus 5. Then if we want to use the definition of convergence, then we have to find a rule for Sn. Sn is the sum of the first n terms. So we go ahead and plug in n equals 1, and n equals 2, and n equals 3, all the way up to n. And we do that and we see what is telescoping about this is that it collapses. Things cancel out, just like a pirate's telescope, which collapses down into a much shorter version. So this is the rule for Sn, and I had told you at the time, and this is still true, this is sometimes very hard to find. In a telescoping series, we can do this without not too much trouble, but this finding a rule for Sn can be hard or impossible. Can be hard or impossible to find, and that's what we're going to do today, is beginning to take a look at some of the cases where finding this rule is impossible. But for the moment we're reviewing what we did before, telescoping, and it was possible. And it was possible in the next one that we did as well, the geometric. Oh, look, there it is, appearing down there. So those two examples, we are able to find the rule for Sn, but that is not common. That is not common. So after that little aside here, let's go back to Sn. We have a rule. So if we want to know whether the series converges, we take the limit as n goes to infinity. So the limit as n goes to infinity of Sn gives us this. That term obviously goes to 0, which leaves us with 1/5. Since the limit exists, the series is convergent, and we say the series equals its limit value. A series equals its limit value. So that was a telescoping series where we applied the definition of convergence. Now, the geometric series was also based on the definition of convergence, but we applied that definition once and for all and found a formula. So for a geometric series, you didn't have to reapply the definition of convergence because it gave us a formula and we could just continue to apply that formula. And so a geometric series looked like this, either from n equals 1 to infinity of a r to the n minus 1, or from n equals 0 to infinity of a r to the n. So if you were to expand that, you would have a plus ar plus ar squared, ar cubed, and so on. And so depending on your choice for sigma notation, both of these are valid representations in sigma notation of this geometric series. And so we had seen this, if we applied the definition of convergence, that there were two cases. If this r, this common ratio r, was less than 1 in absolute value, then the series converged and gave us this as its value. But if that r was greater than or equal to 1, then the limit of Sn did not exist and the series diverged. So now that we have this geometric series rule, as long as we know that we have a geometric series, we do not have to apply the limit again because it is encapsulated in this test. It's already there. So here is an example of something that we might have done earlier as well. If we have this, the sum from n equals 0 to infinity of 2 to the 2n plus 1 times 3 to the 2 minus n, we need to show that this is in fact geometric, and so we put it through using some laws of exponents here into the geometric form. So we can take out a 2, right? This is like 2 to the 1, law of exponents here. We can divide by n, a negative exponent means dividing by 3 to the n. Combining these constant terms gives me 18. Using another law of exponents here lets me write this as 2 to the 2 over 3 all to the n, and 2 to the 2 is of course 4. So there is our ratio r, and since this r is 4/3 in absolute value, well, it's already positive, that is greater than 1, and using that test that this diverges if the ratio is greater than or equal to 1. So this series diverges. Now, as it turns out, these two types of series, the geometric and the telescoping, are the only two that we are going to see, and likely the most famous two, and perhaps the only two at all, where the value of a convergent series can be found. Right? In both of these cases, we had possibilities here to actually give the value. Right? This series was equal to a over 1 minus r in the convergent case. And in our example back here, we said that series was equal to 1/5. And so not only did we know that they converged, we knew the value to which they converged. More typically, that is going to be impossible to do. The rule for Sn is going to be impossible to find, like I mentioned before. And if the rule is impossible, well, then you don't have any way of taking that limit exactly. So the rule for Sn will be impossible, and the value, therefore, will be impossible to find. So what are we going to do otherwise? We're going to resort to pass-fail tests. So those pass-fail tests that we're about to start learning will tell us if a series converges or diverges, but they will not tell us the series value. So going forward in these pass-fail tests, if we're going to apply a test other than the geometric and the telescoping, we will not know the series value. We will only know that it converges or diverges, but if we know it converges, we will not know to what. So we're going to start here by looking at the first of these pass-fail tests, and that is called the nth term test. The nth term test, which is also sometimes called the test for divergence. And so here's the statement of the nth term test. If we have a series n equals 1 to infinity of a sub n, and if the limit as n goes to infinity of the nth term, right? A sub n is called the nth term, hence the name of this, the nth term test, is not equal to 0, then the series diverges. So first thing to point out, please, please, please do not confuse these. This is the limit of the nth term, not the nth partial sum. Right? These are two related series limits, but they are not the same. They are not the same. We're taking the limit of two different things here. So in the nth term test, we are taking the limit as n goes to infinity of the nth term. Now, to prove this, we need a little bit of logic underpinnings, of understanding how logic statements work. In particular, we need to know something about the contrapositive. So let's just take a moment here and figure out what the contrapositive is. Well, not figure out, I'm going to tell you what the contrapositive is. And then when we do the proof of the nth term test, we are going to do it by using the contrapositive. So let's just take a quick moment here and make sure that we understand what this notion of contrapositive statement is. So I'm giving you 4 statements here. I'm giving you 4 statements. Let's go through and read them in turn. Statement 1, if it is raining, then there are clouds. So we know that's true, right? If it's raining, the rain has to come from somewhere, and rain comes from clouds. So statement 2, if it is not raining, then there are no clouds. Well, that's false. It can be cloudy without it raining. If there are clouds, then it's raining. Well, that's not true. That's kind of equivalent to the last one, right? If there are clouds in the sky, it might just be cloudy. And the fourth statement, if there are no clouds, then it isn't raining. Well, that one is true as well, right? Because of the same reason. The same reason that the rain has to come from somewhere, and if it comes from clouds and there are no clouds, well, then it's not raining, right? So statements 1 and 4, are both true. They are both true statements, and they actually are logically equivalent. They are logically equivalent. 4 is what is called the contrapositive statement to 1. And in general, if we have a statement that says, if A, then B, this is logically equivalent to if not B, then not A. So notice 2 things. The order is reversed. The B is with the if, and the A is with the then. But one more thing as well, there's the introduction of this not, which is kind of the contra, right? The not there. So if not B, then not A is logically equivalent to if A, then B. So if you can prove one statement, the other is automatically true. And so that is what we are going to do with the nth term test. We're going to prove this by using the contrapositive statement. So we're going to prove the contrapositive and get for free the statement of the nth term test because they are logically equivalent. So let's go and remind ourselves what the nth term test said. It said, and that's just what was above here on the page, exactly this statement that I've rewritten here. If the limit of a sub n as n goes to infinity is not 0, then the series diverges. So let's just take a moment and remember that the series diverges means the same thing as the limit of Sn, not an, the limit of Sn does not exist. Right? That's the partial sums was in the definition of convergence for a series. So what is the contrapositive? What is the contrapositive? Well, the first thing is that we said that we had to switch places. So the limit goes after the then, and the divergence or the limit of Sn goes with the if, so we switch places. And then what happens as well, we said we have this not. You have to put a not in front. So if I put not does not exist, well, to not does not exist means to exist. And then if I have not equal to 0, well, to not equal 0 is to equal 0. So there is the statement, of the nth term test in its contrapositive form. And we are going to prove the contrapositive, and because these things are logically equivalent, we will automatically get the statement of the nth term test. So let's go ahead and prove this by contrapositive. And we're going to remember this formula that I reminded you of at the top of the lesson here. Sn is Sn minus 1 plus An. So if I subtract over Sn minus 1, I get Sn minus 1 is An. So take the limit as n goes to infinity of both sides. And let's examine what's happening here a little bit. So if the limit exists, we can give it a name. We can call it S. And this is a little bit of a subtlety which turns out to be just fine to use as well. It's true. If n goes to infinity, and we start with Sn, if we're adding up the first n terms, and then letting n go to infinity, well, that doesn't change anything that if we only add up n minus 1 terms and let n go to infinity. Once n goes to infinity, we kind of catch that extra term that was missing in that first sum. So if the limit as n goes to infinity of Sn equals S, then the limit as n goes to infinity of Sn minus 1 equals S also. So that's a little hand wavy, but it is absolutely true, and it's not hard to believe. It's not hard to believe at all from, I think, from my little hand wavy explanation there. So if this limit exists, well, we can apply the limit laws and say that this is the limit as n goes to infinity of Sn minus the limit as n goes to infinity of Sn minus 1. If both of these things are equal to S, well, S minus S gives me 0. And so the limit as n goes to infinity of A sub n has to equal 0. That is exactly the contrapositive statement. That is the contrapositive statement of the nth term test, and so that turns out to be exactly the proof that we need for the nth term test. Now, one little bit of a warning here. The nth term test says only if this limit, the limit as n goes to infinity of A sub n, is not 0, then the series diverges. It says nothing, absolutely nothing about the opposite direction. It says nothing about what happens if the nth limit, the limit of the nth term, does equal 0. It says nothing about what happens in that case. It only tells me about what happens if the limit does not equal 0. And so if it does equal 0, then I know nothing more than I did before. This series might converge, or it might diverge, which puts me no further ahead. So if the limit of the nth term gives 0, the nth term test fails, meaning it is inconclusive. And we will have to apply another test, which we have yet to learn, but we're going to have a litany of other tests that we can apply. So if you get this limit equals 0, right, that is an inconclusive result, and the nth term test has told you nothing. So let's apply that in the next couple of examples and see how this would actually work. So let's apply the nth term test to the following. So here is a series from n equals 1 to infinity of this thing. So the nth term is 3 minus n squared over n squared plus n plus plus 9n plus 20, and if we are applying the nth term test, then we are looking as the limit n goes to infinity of the nth term, not the limit as n goes to infinity of the nth partial sum, right? Not that. That is the definition of convergence, which in certain cases, right, in the telescoping series and in the geometric series might work, but if we're applying the nth term test, that is not what we're looking at. We're looking at the limit of the nth term, so we're looking at the limit as n goes to infinity of this. And using your Cal 1 techniques, you could do a L'Hopital's rule here if you wanted to, because we are getting infinity over infinity as a form. But I think it's much easier just to factor out the largest power of the denominator and cancel them. And so we know that everything here ends up by going to 0. And so this limit gives me 0 minus 1 over 1 plus 0 plus 0, or minus 1. And in particular, minus 1 is not equal to 0. And so if it is not equal to 0, that by the nth term test, the nth term test tells me that this series diverges. The series diverges, okay? So the nth term test is quicker, right? Even if we did do a partial fraction, you might say, well, why don't we try? Why don't we try doing a partial fraction decomposition on this? And maybe you could, and it would be a lot more work, and you would get the same result. So when the nth term test works, it is a nice, quick, typically quick, I mean, you have to evaluate this limit, way to show that the series diverges. So let's do the next example, and the instructions tell us to apply the nth term test, and so that is what we are going to do. So now you'll notice that this looks very similar here. The second example looks very similar, but I've made one little change. I have taken the power down in the numerator from 2 to 1, and so let's see what that does or has as an effect in our limit. So the nth term is still sitting right in front of the sigma here. We are still doing the limit as n goes to infinity of the nth term. So here is the limit as n goes to infinity of this. We are still factoring out the highest power in the denominator, but that creates a change here. Now everything in the numerator ends up by going to 0, and the same things in the denominator do, so I end up by getting 0 minus 0 over 1 plus 0 plus 0, which gives me 0 over 1, or 0. And so the limit as n goes to infinity of the nth term test has given me 0, and so the nth term test tells me nothing. Nothing at all. It is inconclusive. It is inconclusive. And since the instructions tell me just to apply the nth term test, I will stop. I will stop there. I've done what I was told. However, if the instructions say decide convergence or divergence, figure it out, then once we learn more tests, this will not, telling me that the test is inconclusive, will not be acceptable as a final answer, because you have not decided whether this converges or diverges. You've just told me that one test is inconclusive. So in future, once we know more tests, in a case like this, you will need to find another test. You'll need to find another test by going through our list of tests that we are in the process of developing. Find one that will give you a conclusive answer. For the moment, though, we are going to leave it right there, because the goal of this lesson is just to show you how the nth term test works.